So, who first theorized about atoms?
I don't remember. Demetrius DeMarcus III Jr. I forgot his name. I think it starts with a D.
Democrats.
Dimitri DeMarcus III Allen James III Jr. I can't think of his name. I don't know if it starts with a D. Demetrius DeMarcus Allen James III.
No.
Demetrius DeMarcus, you know,
Democrats. It's the third Democrats.
It'd be Democrates.
Democrats.
So,
Can I record this?
I am recording it already. Remove your hand from your head and pay attention. So, Democrates first theorized atoms existed. Yes, over 2,400 years ago, around 400 BC. He basically thought that atoms could not be divided. He thought atoms could not be divided.
I doubt they could back then.
That there was the smallest piece of matter that could not be cut. There existed the smallest piece of matter that could not be made any smaller.
Is it going to be a history test?
Yes, half of it is.
When's the test?
I don't know.
Shit. Give me time.
I'll put it right. You got a pen?
He called them atomus.
What's about my hand?
Why was this theory ignored for 2,000 years?
Because it's irrelevant.
No one really cared.
People
Nobody believed it.
2,000 years. Forever. It wasn't that no one believed it. What was the reason?
Because they couldn't prove it yet.
Aristotle had an alternative theory.
Aristotle.
He was one of the more important ones. So the people are gonna believe the smarter guy.
Yes.
Like that's like putting Mark Zuckerberg beside Albert Einstein, and Albert Einstein saying one thing, and Mark Zuckerberg saying one thing. And even if Mark Zuckerberg is right, Albert Einstein, people probably gonna believe Albert Einstein.
But he is right.
I think, well, maybe not. Right?
He created the atomic solution.
Just because he created something doesn't mean he's smart than Albert.
He did have
I mean, he is.
His IQ was
He's dead
160.
now. Just like Nolan.
Albert Einstein's IQ.
Plato even supported him.
Mr. West.
Yes.
I'm going to grief right now, so I can't possibly work.
What?
My dog died yesterday. Yeah, you gotta taste what's gonna kept the crunch bag in it. Yeah.
So, what was Aristotle's theory?
He didn't get that.
Aristotle's four-element theory is everything was a combination of
Fire.
air, earth, water, and fire.
He was literally here. It's a t-shirt?
What is it?
Who first rediscovered the atom?
Dimitri.
Something Frederick.
And laid the foundation for modern chemistry.
The democracy.
This is nice. The Dimitri guy that Dimitri is
Leonardo da
Bartholomew
Vinci.
James the Third. Leonardo DiCaprio.
It was John Dalton.
Oh no, that's such a plain name. I knew it said something about Fred, but it's hard to read.
In 1803,
In
around.
1814, we took a look.
You know, everything that has been discovered.
Alright, I'll quit talking.
Yes, pretty much.
He thought atoms were also indestructible. Indivisible.
Yeah, the king.
Who
Back up, put on the ground.
who found the first subatomic particle?
Wasn't that the Thompson dude?
No, so what was the orange? The guy
Renegade.
Rutherford.
It was J.J. Thompson.
Thompson.
Oh, right.
Rutherford.
After that, Thompson.
What did he discover?
Adam.
Oh, the neutron.
Electron.
Dang it.
He discovered the electrons. How did he discover the electrons?
The circle thingy. The moving.
Some with electricity.
The dung bell.
He used a cathode ray tube
Okay.
Those things are
filled with a neutral gas. And observed negative particles when current passed through it.
Ain't that little tube thingy?
Yes. What was his model called?
After.
the smallest.
An expensive thingy.
No, that was the first thing.
The Thompson's model?
You like that?
Who would have guessed?
Normally called the plum pudding model. Stop tapping. He thought that an atom was made of a positively charged substance.
What is it?
Not just one.
With electrons scattered like raisins.
This subject's dope.
Wait, what's the question?
Because the example was like the jello with leaves on it.
Which one was the one with the one that could tell you?
Think
The one that like was the pie?
plum pudding.
Yeah, that's what I meant.
The pudding being positively charged. while the plums are negatively charged. That's why it's called the plum pudding model. What is the gold foil experiment?
I don't know.
And then he
The
took
one way they
people-
shot it with the thing.
Oh, they flattened it out and they shot it with that.
Who did it?
Better than a pizza. Oh, that was the Rutherford guy.
So Ernest Rutherford.
Oh, I actually knew him. I didn't know.
It's just,
It's Rutherford. How did physics anything like that?
He fired positively charged alpha particles at gold foil and noticed them bounce off.
And now the particle's the same as the
Helium's nucleus.
heliums.
Two protons and two neutrons.
Give me a neutron.
But most went straight through and without changing direction. This proved two things. One, atoms are mostly empty space. And two, they have a nucleus, a positive nucleus. Meaning all protons are located at the center. All positively charged particles were located at the center. We also give Rutherford the credit for the proton. So proton and nucleus is Rutherford. This isn't in the PowerPoint. James Chadwick. What do you think he discovered?
I don't know if he's done something about that.
Ooh, candle wing.
that must
John.
You are very close
Me?
in mentioning candle wax.
The fire.
So that he used candle wax to discover it.
Oh.
That's it.
Yes, Michael.
But what did he discover? What?
Carbon monoxide poisoning with-
What is the only thing in the atom that we haven't talked about?
electron.
Neutrons.
Neutrons!
I knew it.
It was at the same time.
Shut up.
He discovered neutrons.
What? Michael said they got kicked out of the girlfriend?
He fired alpha particles
Sounds like y'all talking about.
at wax and noticed a neutral particle that had the same mass as protons,
I wonder what the first thought they just.
but no charge. He discovered a particle that had the same mass as a proton, but no charge.
Mr. Webb.
Hmm.
When So these guys, they discovered this. How do you react to that? What do? You just go tell somebody that this is happening?
Write a paper, get it published. Everyone else will then jump on board and try to confirm it. Then they also have like scientific meetings where you see like Einstein, Oppenheimer, Niels Bohr, like photos of where they would all meet up and discuss the theories too.
It's the only meeting.
So between the gold foil experiment and James Chadwick, something interesting happened. So after we discovered basically, I would say the Bohr model too. The Bohr model goes in between these. The Bohr model says electrons are moving in orbits like planets and specific energy levels. So when we figured out the Bohr model was right, or figured out its usefulness, they came up with an interesting theory. So they realized that these electrons are in specific energy levels. They realized that there was a lot of energy. So we take a proton and a proton and put them next to each other. How can two possibly... So what happens when you take a positive charge and a positive charge and put them next to each other?
They detract.
They repel each other. It's like two north sides of a magnet stuck together. In order to keep them together, there has to be a lot of binding energy. There has to be a lot of energy gluing them together. They realized after the Bohr model was completed that there had to be a lot of energy keeping these together. They realized that if you split the atom, a lot of energy would put your mask on. A lot of energy would be released. They theorized about making an atomic bomb. They then did the math. Well, the only way to break up the nucleus is to fire a proton at it. And they calculated that the proton doesn't have enough energy, or you need more energy than released to get a proton to touch it. Because the positively charged proton and positively charged nucleus will repel. You could not get enough energy to make it work. And they went, that's interesting math. There's a lot of energy stored in each atom. Enough to blow up the world. But we can't do anything. It's impossible to make a nuclear bomb. When James Chadwick discovered the neutron, the moment it was discovered, they realized atomic bombs were possible. Because a positive proton would be repelled by the nucleus, if you instead fired a neutron at the nucleus, there would be no repulsion. You could split the atom by firing neutrons at the nucleus. The neutron hits the nucleus, causing it to break apart, and all that energy is released.
This should get with the negative one.
You know something also very interesting?
No, I don't.
There was a... Let's see if I can look up the joke. Y'all won't find it funny. It was nervously said on the minutes before the first atomic bomb. One physicist went to another and went, "Want to take any bets that we blow up the world today?" Because it was honestly extremely worrying. So what is... Let me do a thought experiment. So we have this nuclear bomb. It has a lot of atoms in it, and we fire basically a lot of neutrons at the nucleus. It causes them to break apart. Now, what's the air made of? Atoms, right? Molecules. Where does all these neutrons go? Into the air. And when does the nuclear bomb stop exploding?
No more atoms to be hit.
It was very worrisome. At first, they thought a nuclear bomb, there's a small possibility that when it explodes, the nuclear reaction won't stop at the uranium. It will continue causing the air molecules to create fission and break apart. Basically, the air would be a nuclear explosion, and it would go around the entire world, and the entire world the atmosphere would basically catch on fire. They did a little bit of math and went, nah, it's unlikely.
It's unlikely. I mean, it won't happen.
But it was really interesting that for a little bit they had to really confirm that before they did the nuclear bomb, they got very confident that it would not catch the air on fire.
Confidence.
Imagine being the guy who made the math mistake and. Yes.
Think about it.
Then we have Erwin Schrödinger.
If they would have blown the world up, then the beds wouldn't have mattered. They'd be dead.
They would've blown the world up.
That's why it was a joke.
So like, what happened? Did they survive? Did they live?
Well, everyone's still alive. I mean, it would have destroyed all life on Earth.
No, no, like,
An asteroid.
Well, maybe some life would have survived.
Bunkers.
Worked on quantum mechanics.
God could have been like, he.
I could have just destroyed the world. Could have been that.
And helped develop the modern day wave model, also known as the electron cloud model.
Ooh, electron cloud. No.
So, electrons are in clouds. We call them orbitals, but they are just really they are regions where we have a 90% chance of finding the electron. Alright, let's go over now isotopes. So, atoms contain protons, neutrons, and electrons. Protons and neutrons are found in the nucleus. The nucleus contains most of the mass of an atom. Electrons are distributed around the nucleus in energy level shells or orbitals, which make up the electron cloud. So, an energy level. Let me pop up this image. So, a shell is another name for energy level. An energy level is made up of sub-levels, or sub-shells, and then each of these are orbitals. So all the p orbitals make up a subshell, and everything on energy level 2 makes up a shell. So all three of these would be a part of the same subshell. There's s orbitals, there's p orbitals, there's only one s orbital, there's 3p. So an orbital is the individual one, and the shell is the entire energy level. I don't think in this class I test over that depth, just to give you an idea. Altogether, that's the electron cloud. The outermost electrons in the shell, farthest from the nucleus, is called valence electrons. So the first subatomic particle discovered in 1897 by J.J. Thomson using the cathode ray tube was the electron. It has a negative charge of -1. Its mass is really, really tiny. 0.0005 atomic mass units. Electrons are located in specific energy levels, which make up the electron cloud. Electrons in the outermost energy level are called valence electrons. Valence electrons are the only electrons that deal with reactivity. The proton, it was observed by E. Goldstein, but Rutherford is also given some credit because he discovered the nucleus. I don't test over Goldstein. It says it right here, the second thing. Rutherford is given the credit for showing that atoms contain both negatively and positively charged particles. It wasn't observed until Goldstein observed it, but Rutherford is often given the credit because he simply showed the nucleus existed. It has a charge opposite of, it's equal but opposite in sign of the electron. It has a charge of +1. The electron is -1. And it has a mass of 1 atomic mass unit. The electron is 0.0005 AMUs. The proton is 1 AMU. If we look at it in grams, that's 1.673 times 10 to the -24 grams. So a billionth, and thousandth, and tenth. If you add all those together, a billionth, thousandth, and tenth, I believe is the correct of a gram. So really, really small. If we look at the neutron, it is only ever so slightly heavier. The third major subatomic particle discovered by James Chadwick has no charge, it's neutral, and has about the same mass as the proton. The neutron is ever so slightly heavier, but we usually treat the protons and neutrons as having the exact same mass. Cody! Y'all wake up. Michael, you too. So, isotopes. Isotopes are atoms of the same element. They have the same atomic number, the number of protons. So each atom of the same type has the same number of protons. It's the protons that determine what atom it is. Isotopes, though, have different number of neutrons, and therefore a different atomic mass. So isotopes are atoms of the same element, but having different number of neutrons and thus mass. We write the symbol for an isotope in this form. On the top left, we have mass number. Mass number is just going to be the number of protons plus the number of neutrons. In the bottom left, we write the atomic number, the number of protons. And then we put the element symbol in the middle. So, for example, krypton, 94. We'd write like this. Oftentimes, we'll leave off the bottom left number, but for this class, we don't. You'll often see the bottom left number because KR is always 36. It's redundant to put 36 in the bottom left too, if you know what KR is. But usually, we write both numbers so that you don't have to look at the periodic table to figure out what number it is. There are naturally occurring isotopes. Every element has naturally occurring isotopes. Hydrogen has 3. The most common form of hydrogen has only 1 proton and 1 electron. all hydrogens have one proton and one electron. The only thing that changes is the number of neutrons. The most common type is 99.985% of all hydrogen atoms have no neutrons. It's called protium. Deuterium has one neutron and is very uncommon, 0.015%. And tritium is even less common than that. 0.0001% of all hydrogen atoms have two neutrons. They look like this. So this is known as symbol notation or isotope notation. This is known as symbol notation. There is another way to write it. It's called hyphen notation. You write the name of the element, hyphen, and the mass number. So this would be chlorine 35 and chlorine 37. You might have heard of carbon dating. Have y'all heard of carbon dating? So what carbon dating is cosmic rays from the galaxy and the universe and even from the sun are constantly bombarding Earth. Earth's atmosphere is made up of what gas was the number one gas? Nitrogen. So these cosmic rays will come into and hit the nitrogen atoms and cause a proton to break off. You look at your periodic table, you'll see that nitrogen is just one proton above carbon. And when it breaks off, it turns into nitrogen turns into carbon-14, which is radioactive. So the only way that carbon-14 on Earth is made is in the atmosphere due to cosmic rays hitting the atmosphere. You're constantly breathing in this radioactive isotope. It's very, very rare though. But while you're alive, and that's the only way you can get it, while you're alive, you're constantly eating plants that have carbon-14 in it. And Thomas, wake up. Lift your head up. You're constantly breathing in air that has carbon dioxide with carbon-14 in it. You're constantly getting carbon-14 into your body. It's in very, very small amounts, but while you're alive, you have a certain percentage of carbon-14. When you die, you stop getting carbon-14 into your body, and that carbon-14 will eventually decay, and you'll no longer have any carbon-14 in your body. We can look at the ratio of carbon-14 to carbon-12, and thus to figure out how long you've been dead for. So naturally occurring carbon consists of 3 isotopes, carbon-12, carbon-13, and carbon-14. Yes? Mm-hmm. So, carbon-12, carbon-13, and carbon-14.
Why did you check the bottom?
Because that's how you write it.
Yeah, the atomic number.
Yes. So the 6 is the atomic number. So number of protons, they all have 6. When we talk about isotopes, we usually talk about neutral ones. In order to be neutral, it has to be the same number of electrons as protons. So they all have 6 electrons. The only thing different between isotopes is the number of neutrons. So how many neutrons does carbon-12 have? So the mass number is the number of neutrons plus the number of protons, and that's equal to 12. The bottom one, yes, is the number of protons, and that's equal to 6. If you subtract these, the protons cancel out, and we're just left with n equal to 6. So it has 6 neutrons. Again, doing the same thing for carbon-13. So neutrons plus protons equals 13. The protons is 6. We subtract these. Protons cancel out, and the number of neutrons is 7. So basically, we just subtract these numbers to get the number of neutrons. 14 minus 6 is 8. So carbon-14 has 2 additional neutrons than carbon-12. An atom of zinc has a mass number of 65. The number of protons in the zinc atom is what? Do you have y'all's periodic table?
So what is it now? 35. I'm guessing. 40, 50.
So zinc is here.
Good.
So zinc has an atomic number of 30. So the number of protons for zinc, protons would be equal to 30. And it said that the mass number is 65. So the mass number is 65. How many neutrons does it have? 35. So 30, that's your protons, plus 35, your neutrons, has to equal your mass number. And how many electrons does it have? It's neutral, so it has the same number of electrons as protons. What is the mass number of zinc isotope with 37 neutrons? So what is mass number of zinc with 37 neutrons?
The triangle thingy.
Put your head up, Cody. So the protons is 30. The neutrons is 37. So the mass number would be 67. So zinc with 37 neutrons would be called zinc 67. Or 67 zinc, like this. This is symbol notation. Yes. This is hyphen notation. This is hyphen. This is nuclear. Notation. Or symbol notation. Michael, lift your head up. Or sometimes just isotope notation. By the way, we are going to be using these in mathematical equations.
That was the physics.
We still are going to do nuclear equations. It's important, you know, isotope notation. So, atomic mass, listed on the periodic table, gives the average atom of each element compared to carbon-12. Average atom based on all the isotopes and their abundance percentage. We're not going to be calculating atomic mass in this class. So there are two categories, unstable and stable. Unstable isotopes are also known as radioactive isotopes. They continuously and spontaneously break down and decay into lower atomic weight isotopes. Stable ones do not naturally decay, but can exist in natural materials in different proportions. Radioactivity is the process in Thomas and let's y'all set up. Michael, keep your eyes open. So radioactivity is the process by which nuclei spontaneously undergo transformation to other isotopes with the corresponding Cody, lift your head up, with the corresponding release of radiation. Have you ever heard of half-life?
Mad Max?
So a half-life is the time it takes for half the material to decay. So half-life is the time it takes for half the material to decay.
So apples, for instance, when it turns brown, is it already?
No, this is for radioactive. Half the radioactive material. To decay. So let's say that we have an element that has a half-life of 1 hour. Suppose a radioactive isotope if we started with 1 kilogram or 1,000 grams, how much would be left after 10 hours? So we started with 1,000 grams.
Well, you said
That's 500
you wanted it to be
250.
0 because if the
125.
half-life is an hour, and
So,
half of it takes it to decay, so that it would
In 1 hour, half of it will decay and we'll only have 500 grams. Another hour, so the 2-hour mark, half of it decay and we have 250 grams. Another hour, half of it will decay, we have 125 grams. And then after that,
62.5.
so 62.5.
31.25.
Then after that, at 5 hours will be 31.25. Then 15.625 to 6 hours. Then 7.8125 grams at the 7-hour mark. Then the 8-hour mark will be 3.90625 grams. And then at the 9-hour mark, we'd have 1.953125 grams. And finally, at the 10-hour mark, after 10 hours, we'd have less than a gram. 0.9765625 grams. So after 10 hours, or a kilogram, 1,000 grams, would decay to less than 1 gram. By the way, is there an easier way of doing this?
Always go to your wife and
We could do 1,000 times 2 to the negative t, where t is your time. So 1,000 times 2 to the negative 10 will give you the result. Because we're halving by, so the negative tells us it's 1,000 divided by 2 to the x,
Wouldn't it be
or t. So if you wanted to figure out how much would be left after a full day, you could do 1,000 times 2 to the negative 24.
that would be like divided by 2?
The negative is the same thing as dividing by 2. So the exponent. 5.96 times 10 to the negative 5 grams.
A minute and 6.